Hello and welcome to helpyourmath.com. In this video, we are going to look at examples of solving absolute value inequalities. In the first example, you can see we have the absolute value of 4m minus 9 being subtracted by 5 is greater than or equal to 16. Before we decide if this is a conjunction or a disjunction, we want to isolate the absolute value, preferably on the left-hand side, which is where it already is. The other thing that's on the left-hand side, as we can see, is this minus 5. So the first thing I want to do is add 5 to both sides, and that will get the absolute value by itself. Okay, so now I have the absolute value of 4m minus 9. I keep the absolute value bars because I haven't done anything with them yet. Is greater than or equal to 16 plus 5 is 21. Now that we have the absolute value isolated, now we want to consider, is this a conjunction or a disjunction? Well, an absolute value will be a conjunction if we have a less than or equal to. And it will be a disjunction if we have a greater than or equal to. In this case, since it's greater than or equal to, this would be a disjunction. What that means is that we're going to have two separate sets of solutions. We're going to have some that are bigger than or equal to some number and some that are smaller than or equal to another number. And what we know is that what's inside the absolute value, this value here, 4m minus 9, once we take its absolute value, it needs to be greater than or equal to 21. So the first case is that 4m minus 9 is greater than or equal to 21 itself, because if we have a number that's bigger than 21, and then we take its absolute value, that will also be bigger than 21. It's a disjunction, so we use the word or. The other possibility is that what's inside the absolute value could also be a really big negative, right? Because if it's like negative 100, but then we take the absolute value, that's bigger than 21. So the other possibilities are that 4m minus 9 is less than or equal to negative 21, because that's where all of those solutions, once you take the absolute value, those will be bigger than 21. Notice that for the negative case, I also had to flip the inequality symbol because we're considering the numbers that are now smaller than negative 21. That would be our negative 22, negative 23, negative 100, etc. From here, we solve each inequality separately. So I'll add 9 to both sides. And I get 4m is greater than or equal to 30. Then I'll divide both sides by 4. 4 doesn't go evenly into 30. So I can just say greater than or equal to, I can divide them both by 2 and get 15 over 2. If you want to, you could rewrite it as 7.5 or 7.5. That might make the graph a little bit easier, but it doesn't matter. You can leave it as 15 over 2. Okay, so the first set of solutions are when the variable is bigger than or equal to 7.5. What about the other set? So we're going to add 9 to both sides to isolate the m. This will give us 4m. Oh, I just added 9, so I don't need to include a minus 9 anymore, is less than or equal to negative 21 plus 9 is negative 12. Then we'll divide both sides by 4, and we get m is less than or equal to negative 3. So we have the two possibilities. We have m is greater than or equal to 15 over 2, and then we use the word or for the disjunction, m is less than or equal to negative 3. This is step 1. Now step 2 says, okay, graph your solution. So let's see, I need 7.5 and I need negative 3, so I need a fairly big number line here. I'll go negative 4, negative 3, negative 2. I don't know why my numbers are getting smaller, but there they are. As long as my increments look okay. 4, 5, 6, 7. Let me get rid of this arrow if I can. Yeah. Great. 8. Okay. Negative 3, and we use a closed circle because negative 3 is itself a solution, and all of the solutions here are to the left of negative 3, smaller than negative 3. If you want to, you can check one of those numbers. So plug in negative 4 to the original function. So plug in negative 4 to the original inequality and see if it does in fact produce a true statement, which hopefully it does. And then we have 7.5, that's right in between 7 and 8. Also a closed circle, meaning 7.5 is itself a solution, and the arrow is going to the right, all the numbers that are bigger than 7.5. So there's the graph, and the last step is to write the answer in interval notation. For interval notation, to say that some of the solutions are bigger than or equal to 15 over 2. We put a bracket to the left of 15 over 2, and then it would go to infinity. I'm going to put the smaller one in front, just like we would see on that graph. The smaller numbers are to the left. I think here technically you could do either way, but just to be consistent, I'll put the m is less than or equal to 3 on the left. That would be negative infinity to negative 3. And that would be the 3 different ways to represent the solution set for this absolute value inequality. I want to look at one more case. In this case, let's see what happens when we isolate our absolute value. First, we need to subtract 4 from both sides. And then we get the absolute value of 3x plus 8 is less than 7. This time we have a less than, and we may recall that a less than means we have a conjunction. When we have a conjunction, we can actually just create one single compound inequality instead of looking at 2 separate inequalities. With a conjunction, all of the solutions lie between 2 numbers. So we're going to have a number bound on the left and a number bound on the right. And these numbers, the numbers that are closer to 0 on a number line than 7, will lie in between negative 7 and positive 7, right? Because all of those numbers, negative 6, negative 5, negative 4.5, 0, those are all a smaller absolute value than 7, which is what this says it wants. So to set up the compound inequality, and we can only do this for a conjunction, we're going to say that negative 7 is the minimum for this 3x plus 8, and 7 is the maximum. And then from here, when we go to isolate x, we're isolating x in the middle, and whatever we do in the middle, we have to do to the left side and the right side. So this time it's a triple. First, I want to get the plus 8 gone, so I'll subtract 8 from all 3 sides. And then we have negative 7 and negative 8 make negative 15 is less than 3x plus 0 is less than negative 1. And now I want to divide everything by 3, so I divide by 3 on the left, the middle, and the right, and I get negative 5 is less than x is less than negative 1/3. And that would do it. If you decided to separate and consider the 2 cases, the positive would be 3x plus 8 has to be less than 7, and 3x plus 8 would be greater than negative 7. When you say your final answer, you would include the word and because it is a conjunction. When I go to graph my solution set, I know I need to have negative 5 here, so I'll start with negative 6. And negative 1/3 lies in between negative 1 and negative 2. Negative 1 and 0. I'm writing negative 2 and saying it at the same time. Not a good idea. Negative 5 will have an open circle. This negative 1/3, which is in between 0 and negative 1, will have an open circle. And we will connect them with a bar. We don't put arrows on this because it is bound by negative 5 and negative 1/3. Nothing outside of that range is a solution. So we don't put the arrow to say like it would keep going this way because it doesn't. It stops at negative 5 and negative 1/3. That would be it. We just connect it with a bar. That bar represents that all of the numbers below it are solutions. For interval notation, since this is a conjunction, we just have one interval of numbers and it's bound by negative 5 and negative 1/3. We do not include the endpoints. This was a look at solving absolute value inequalities. Thank you for stopping by.